Good morning, sir. Today I present my project on automatic plant disease detection using artificial intelligence. Plant diseases cause big losses in crops worldwide and affect food supply and farmers' income. Usually, experts need to check plants to find diseases, but this takes time and experts are not always nearby, especially in far areas. My project solves this problem by building an AI system that can quickly detect plant diseases just by looking at leaf images. This technology can change farming by giving farmers a fast, correct, and easy way to find diseases. It can help farmers everywhere protect their crops and get better harvest. The foundation of my project is transfer learning, a powerful machine learning technique. Instead of training a model from scratch, which requires massive datasets and computational resources, I used a pre-trained ResNet 18 model that had already learned to recognize patterns from millions of general images. Think of this as hiring an experienced art expert and specializing them in a plant disease recognition that they already understand shapes, colors, and textures so they can quickly adapt to this specific domain. This approach allowed me to achieve high accuracy with limited training data and computational resources. I selected ResNet 18, a 18-layer deep convolutional neural network, as my base model. This architecture is particularly effective because it uses residual connections that help train deeper networks without the vanishing gradient problem. The model was originally trained on ImageNet containing 1000 object categories. For my project, I kept the future extraction layers frozen to preserve their learned knowledge and replaced only the final classification layers with a custom head designed specifically for 15 plant disease categories across pepper, potato, and tomato plants. The training process involved showing the model thousands of labeled plant images in batches. During each training epoch, the model made predictions, calculated errors using cross entropy laws, and adjusted only the custom classification layers weights using the Adam optimizer. I used data augmentation techniques like random flipping and rotation to make the model robust to variations in real world conditions. The model was trained for only 5 epochs, demonstrating how transfer learning enables efficient training while preventing overfitting through techniques like dropout regularization. The trained model achieved remarkable 90% accuracy on the test set, with some disease categories like tomato yellow leaf curl virus reaching 97% detection rate. The system can distinguish between 15 different disease conditions with high precision. This technology can be deployed as mobile applications, enabling farmers to photograph diseased leaves and receive instant diagnosis. Early detection allows for timely intervention, reducing pesticide use, minimizing crop losses, and promoting sustainable agricultural practices. This project demonstrates how AI solves real-world agricultural challenges effectively. We begin by installing and importing all necessary libraries. We use PyTorch for deep learning, Torque Vision for computer vision tasks, and sklearn for evaluation matrix. Matplotlib and Seaborn help with visualization, while the Kaggle library allows us to download our dataset. Here we handle our dataset from Kaggle. After downloading, we apply the crucial 80-20 split, that is 80% for training and 20% for validation. This ensures our model learns from one dataset while being tested on completely unseen data, preventing overfitting. Here we set up our data pre-processing pipeline. We configure GPU acceleration for faster training and define two types of transformation. For training data, we use data augmentation, including random horizontal flips and 20-degree rotation to make our model robust to real-world variations. All images are resized to 224 cross 224 pixels, which is the standard input size for ResNet models. For validation data, we apply only basic pre-processing, resizing, and normalization to evaluate our model on original unmodified images. We normalize using ImageNet statistics because our pre-trained ResNet was originally trained on ImageNet data. Our dataset contains 15 different plant disease categories across pepper, potato, and tomatoes. For efficient training, we use 10,000 images for training, 2,000 for validation. Now let's visualize our data. We display 16 random samples from our validation set to understand what our model will learn from. Each image shows the actual plant leaf with its corresponding disease label. Note that visual differences between healthy leaves and various diseases like bacterial spots and viral infections. We reverse the normalization process to display images in their original colors. This is the core of our transfer learning approach. We load a pre-trained ResNet 18 model that has already learned to recognize patterns from millions of ImageNet images. We freeze all backbone layers to preserve this learned knowledge and replace only the final classification layer with our custom head design specifically for our 15 plant disease classes. Our custom classifier has 256 hidden units with a relay activation function, 40% dropout for regularization, and a final output layer matching our 15 disease categories. Only these new layers will be trained, making the process very efficient. Now we begin with training. We use cross entropy loss for multi-class classification and Adam optimizer with learning rate 0.001, optimizing only our custom classification head. The training loop has two phases. In training mode, we compute predictions, calculate loss, and update weights through back propagation. In evaluation mode, we test only validation data without gradient computation to monitor real performance. Watch the excellence progress, starting at 84.75 accuracy in just the first epoch and rapidly improving to 90.2% by epoch 5. The loss consistently decreases, showing stable learning. Now for the comprehensive evaluation on the complete test set of 4134 images. Our model achieves an excellent 90.08% accuracy with a low test loss of 0.294. This outstanding performance confirms that our transfer learning approach successfully generalized to completely unseen data. The loss plot shows consistent decrease from 1.11 to 0.43, demonstrating stable learning. The accuracy plot reveals steady improvement from 84.75 to 90.20% during training. Most importantly, our final test accuracy of 90.08% matches the training performance, proving no overfitting occurred. The confusion matrix reveals excellent diagonal dominance, indicating correct predictions across most classes. Notably, success include pepper bell healthy with 100% accuracy and tomato yellow leaf curl virus with 96% recall and tomato healthy with 92% recall. Some confusion occurs between visually similar diseases like different tomato spots, which is expected and shows the model is learning meaningfully patterns rather than memorizing.